Hi everyone, welcome back. I today brought a very special guest. This is Texie, my 10-week-old puppy. And yeah, we have another update for you from an experiment that we finished this past semester. So if you remember, a while ago I talked about how we used machine learning to find out in which sequence we should present visuals to students in intuition trainings. And as a reminder, intuition trainings expose students to many visuals in very simple tasks like, do these two visuals show the same molecule? And the question is, how should we sequence these visuals? Typically, what we do when we create instructional sequences, we think about what we want students to pay attention to. Say I want students to pay attention to the color of spheres, to learn that red stands for oxygen, and to letters in Lewis structures to learn that O stands for oxygen. Then I could give students examples where red and O co-occur and other features vary. And based on this principle, experts generate learning sequences. But in doing so, we make a lot of assumptions about what students initially notice. And what if these assumptions are wrong? In that case, it can be very difficult for experts to put themselves in the shoes of novice students, and that is what we call the expert blind spot. And that can be counterproductive when I'm creating instruction for novices. And indeed, as you may know from some of my other videos, I found that intuition activities are usually most effective for students who already have some good idea of what visual features like colors and letters mean. So we used a machine algorithm that, because it's a machine, doesn't make any assumptions about students to generate a sequence of visuals for novice students. And for details on how we found this sequence, I'll add references below to my earlier videos that have some more information about this. So we tested the sequence in an experiment where 45 chemistry students worked with ChemTutor, an instructional technology for chemistry that we developed in my lab. In ChemTutor, they first worked on some regular problems where they used visuals to solve problems, and then they worked on intuition activities. Half of the students got intuition activities that contained visuals in the machine-generated sequence, and the other half of the students got intuition activities based on the expert-generated sequence. And we assessed their intuition skills before and after. And here's what we found. This graph shows students' performance on the regular problems on the x-axis and the pre-post intuition gains on the y-axis. The blue line represents students who worked with the expert-generated sequence, and the red lines show students who worked with the machine-learned sequence. And what you can see here is that for those students who had low performance on the regular problems, so those who made many errors and seemed to not have a good understanding of the visuals, the machine-generated sequence actually yielded higher learning gains than the expert-generated sequence. By contrast, the high-performing students benefited more from the expert-generated sequence. So this means that machine learning helped us come up with an effective sequence for weaker students, which is something that is actually very difficult for experts to do because they may have difficulty empathizing with the weaker students. So in a way, machine learning helped us overcome the expert blind spot.